to determine the cooling process of an object. So this law was named after Isaac Newton in 1701. Interestingly enough, his original law is not used today. It's been refined by scientists. The original law states the cooling rate is proportional to the temperature difference between object and surroundings. So this gives us a kind of base of the law that we know today. So this gives us the idea that the bigger temperature difference between an object in the room, the faster the object will cool down.
Alright, I'm Justin Ryan. This is my introduction for Newton's Law of Cooling. So the law does not account for heat loss from other methods like radiation or conduction. The rate of cooling of an object slows down as it approaches the temperature of its surroundings. Kind of like take food out of the oven. Once it gets closer and closer to the room temperature, it's going to start slowing down on how it cools. The law states that the rate at which an object cools is directly proportional to the difference between its own temperature and the temperature of its surroundings. So obviously, if you have hot food and you take it outside on a cold day, it's going to cool off a lot quicker than it would if it was just like lukewarm food in a moderately air-conditioned house.
Newton's law of cooling is based on experimental observation rather than strict theory. The law assumes the cooling environment stays at the constant temperature during the process. It applies best when the temperature difference between the object and its surroundings is small. The real-world deviations occur when air movement, radiation, and material properties affect heat loss. The law is often used to simplify complex heat transfer problems in engineering and science.
Newton's law of cooling was proposed by Sir Isaac Newton in the early 18th century. It describes how the temperature of an object changes over time when it is exposed to an environment with a different temperature. The greater the temperature difference, the faster the object will cool off. And as the object's temperature gets closer to the surroundings, the cooling of the object will slow down.
Although there are many related fields to Newton's law of cooling, the one I chose to review is forensic science, as it directly relates to the law in an interesting way. So forensic scientists actually use this to help estimate the time of death. So they apply his law by measuring the body temperature and then the room or like the air that's around them to help estimate how long the body's actually been cooling.
So related fields, we have thermodynamics, which is a branch of physics that deals with heat, work, and temperature, and their relation to energy, irradiation, and physical properties of matter. Even though Newton's law of cooling is an empirical equation, it does not comply with some thermodynamic laws in the aspect of second law of thermodynamics, heat transfers from hot to cold bodies independently.
On the related field subject, Newton's law of cooling can be applied to environmental studies and climate science. This law helps explain how nature and artificial surfaces heat and cool in their surroundings. Scientists use it to model how quickly land, water, or air masses lose heat after sunset. It also helps explain the urban heat island effect, where cities stay warmer than rural areas due to slower cooling rates.
Okay, the related field that I chose was mechanical engineering because it is directly related to Newton's law of cooling. In mechanical engineering, engines and machinery generate vast amounts of heat. This law helps estimate the cool down rates to make sure that parts in the engines don't overheat and they're able to maintain their performance. Mechanical engineers apply this law to their everyday jobs to prevent overheating and mechanical failure, ensure safety, and increase product performance.
There are many relevant scientists, but the one that caught my attention the most was Jean-Baptiste Joseph Fourier, who was a French mathematician and physicist, and he was born on March 21st, 1768, and he unfortunately died on May the 16th, 1830. He attended many French schools, including military school, where he actually decided to become a teacher since he enjoyed it so much. He, outside of the classroom, he decided to go to Egypt, and he dedicated a lot of time discovering and studying Egyptology, and this opened many pathways for him. He actually became a secretary at the institute, a science institute in Egypt. And all of this is very amazing for him because even though he had a rough upbringing and he was orphaned at the age of 9, he still went on to accomplish many great things. He passed Egyptology. He was also known for his analytical theory of heat, and he also made a notable influence on heat flow equations. And now I'll pass it to my next.
So for my relevant scientist, I have Joseph Black. He was an 18th century Scottish physicist and chemist. He's known for his work on heat and thermodynamics, particularly his discoveries of latent heat and specific heat capacity. While he did not directly study or challenge Newton's law of cooling, his work provided the essential concepts needed to understand why the law is not universal and why different substances cool at different rates.
My relevant scientist is Sir Humphrey Davy. Sir Humphrey Davy is a British chemist and physicist born in 1778. He is known for his studies on heat and energy. He demonstrated that heat is a form of energy and not a material substance. His discoveries helped lead scientific thought toward the modern and understanding of thermodynamics. His work supported later scientists into refining heat transfer models like Newton's law of cooling. Famous for discovering elements like sodium and potassium using electrolytes.
Okay, lastly, the scientist that I chose is George Wilhelm Richmond, and he was born in 1711 and was best known for working on temperature measurement and heat transfer. The fields he worked in included heat, electricity, and atmospheric physics. He tested and expanded on Newton's law of cooling by experimentally studying how quickly objects lost heat to their surroundings. He improved temperature measurement techniques by building better thermometers, which ultimately allowed scientists to measure temperature differences more accurately, which led to the verification of Newton's law of cooling.